Welcome back to our Airline Planning and Optimization course. In this last video lecture regarding the aircraft maintenance planning problem, we're going to see the work that was developed by a PhD student of mine, Qichen. In particular, we're going to see how we can use a dynamic programming approach to solve the aircraft maintenance check scaling problem, considering the long-term planning and having the flexibility to include all the operational constraints that we have discussed in the previous video. But let's recall what is the maintenance check scaling problem about. The problem consists in defining the starting dates of the maintenance checks in such a way that we minimize the wasted interval associated with each check that we have to schedule. I remove now the part of the description that refers to a given set because we don't have this set being provided to us in the beginning. In this long-term planning, let's say 2, 3, 4 years time horizons, it is not possible to define beforehand what are the number of checks that we have to schedule. This will depend on our decisions in the initial years. Actually, what we really want to do is to reduce this number of checks that we're going to have in our final schedule by exploring the predefined interval as much as we can for each one of the checks that we're going to schedule. With dynamic programming, as we break down our problem into several stages that could refer to the time steps that we have to consider in our decision. So it will be possible to determine the number of new maintenance checks that we need in the future, given the actions that we're going to take at each time step. So we're going to know and define the number of checks that we have to schedule by solving the check scaling problem, going from stage to stage. The problem, as in the previous video lecture, is subjected to the considerations that we have discussed before. But now we do not have a due date associated with each check. We don't have the checks, correct? So we do have to replace this information by the information regarding the predefined interval associated with each type of check. And we'll determine the due dates as we schedule a maintenance check for a given aircraft, and then we determine what will be the due date for the following check of the same type. So this is the problem, and how can we formulate this problem using a dynamic programming approach? We need to define what are the states, what are the actions, and what are the transition functions to go from one state to the other state. Remember, our goal is to minimize the interval loss that we have associated with each maintenance check that we schedule. Starting with the definition of the state. Which information do we have to consider to define a state in our dynamic programming framework? The obvious approach is to store information about every single aircraft in our fleet. These aircraft have attributes, and these refer to the three types of maintenance checks that we're going to consider: the A check, the C check, and the D check. That is, for each aircraft and for each check, we have to store what are the calendar days, the flight hours, and the flight cycles since the last check of the same type, with the exception of the C check, in which we only have to store the calendar days. By doing this, it means that per aircraft we have to store 7 attributes. And if we have 10 aircraft in our fleet, we need to store 70 features describing each state. And if we have to do this for 50 aircraft, we will have 450 features to store for each specific state in our dynamic programming framework. This is a huge number that will complicate our modeling approach. Imagine storing all these features for all states in our dynamic programming tree of possible states. Of course, we can reduce the number of states by considering a smaller time horizons and modeling time stages, so time jumps, that happen every week and not per day. But if we want to really model our maintenance check scaling problem into detail, considering all the operational requirements that we have discussed in the previous video, we want to model 4 to 5 years long term, but we want to model day by day, because every day may have different conditions. And we can then have more than 1500 time stages with multiple possible states at each stage. And if we have a fleet of 50 aircraft, for all these states, we have to save these 450 features. So imagine the memory that we need to store all this information. The next step is to define the actions. So we are at a given stage, at a particular state in that stage. And we want to define which actions we have available. If we have a single aircraft in our fleet and one A check and another C check slot per day, we do have 3 possible actions: to perform an A check maintenance in that aircraft, to perform a C-check maintenance in that aircraft, or to not perform any maintenance check on that day and keep the aircraft flying. Actually, we do have a fourth option, which is to merge the A-check into a C-check, which is a common practice if that's desirable for the airline. But we'll leave that out of our discussion in this lecture. For a single aircraft, it is simple to understand the options, but we're rarely going to work in the case that we only have a single aircraft in our fleet. Actually, in that case, perhaps we'll not even need an optimization framework to solve the problem. So the example that we have here in this slide is the example with 3 aircraft, only 3 aircraft, and again 1 A-check slot and 1 C-check slot per day. In this case, we may have 10 possible solutions for each state that we are, starting with all 3 aircraft remaining in operation, so no maintenance check being performed, to all combinations of A-check and C-check and no C-check between all the 3 aircraft in our fleet. This number of possible actions will start to increase as we increase the number of aircraft in our fleet, make it hard to model all possible options. Imagine our dynamic programming's tree of states, actions and outcome states. It will be a huge amount of branches and branches that will be almost impossible to model. So it doesn't look promising, but let's finish this overview by looking at the transition function. In our aircraft routing problem, this transition function was the calculation of the profits associated with each option of flying between airports. In this aircraft check scaling problem, the transition function is the update of the attributes per aircraft, or more specifically, the usage parameters associated with each aircraft. So if we decide to perform an A-check to a specific aircraft in our fleet, we have to reset the A-check usage parameters for that aircraft. The aircraft won't accumulate any flight hours or flight cycles in terms of the usage parameters of the C-check, but we'll have to increase the number of calendar days for the C-check. On the other hand, if we decide to perform a C-check, then are the usage parameters of the C-checks that have to be reset to 0, and the A-check's calendar day parameters is increased by 1 day for each day that we remain doing the C-check. If no checks is to be performed, then we have to update all usage parameters for both A-checks and C-checks, including the flight hours and flight cycles associated for that specific day. In this case, 10 flight hours and 5 flight cycles. In all the cases, we'll also have to add 1 calendar day to the usage parameter of the D-check, but in this example, we are disregarding the D-checks. This transition function is not hard to understand, but you can start imagining the net of possible outcome states that we're going to have associated with each initial state and action that we have available. So it seems that dynamic programming is not a good option to model this problem. Why is that the case? Well, the problem is the 3 curses of dimensionality, as we have discussed in the previous lecture. These refer to the size of the state space, as we have discussed a couple of slides ago, the action space, and also the outcome space. So it is impossible to solve this aircraft maintenance check scaling problem with the traditional dynamic programming approach. Indeed, it is. So what Qichen has done was to adapt the traditional dynamic programming approach with some additional features or algorithms to help us to solve this problem in a very efficient way. Let's see how Qichen did this. Well, to address the multidimensional action vector, we're going to prioritize our aircraft for both A-check and C-check. We're going to see that in the next slide. Referring the outcome sequence, we're going to look into a forward induction. That means that we are not going to start from the end and then move backwards as we did for our aircraft routing problem. We're going to start from the beginning and moving forward. There are 2 reasons for this forward induction approach. The first one is that we're going to make some selections of the outcome states and not going to explore all the outcome states. And the other reason is that in this problem, we don't have really a final state which we really know what will be the contribution value there. So contrary to this aircraft routing problem, in which we started at the end and then we moved backward, knowing exactly what was the value at the end, 0. In this case, for the aircraft check scaling problem, we don't know this value, so we cannot move backward, so we're going to start from the beginning. The third consideration that Qichen did was to look into the multidimensional state vector. And for this, we're going to discretize our states and aggregate these states And this, together with the forward induction, will allow us to just visit a few outcome states, as I already mentioned. But to do that, we need to have a new algorithm that checks the workability or the feasibility of future states. We're going to get into detail in the next slides in each one of these three additions that Qichen added. So let's start with the priority. So let's assume that we do have 3 aircraft in our fleet, an orange, a blue, and a yellow. The orange, according to our calculations, will have to perform a C-check in the coming 14 days. The blue one has 90 days to perform this C-check, while the yellow one has to do in the coming 5 days. So if we have this scenario, we can consider that the yellow aircraft has a higher priority than the orange one, and this one has a higher priority than the blue one. So if I have a C-check slot, perhaps it's a good idea to consider only the yellow aircraft to use that slot for the C-check. So I'm going to reduce the action space, as we defined a few slides ago, into a smaller action space, because for the C-check I only have 2 options. Either to not perform any C-check in none of the aircraft in my fleet, or to perform a C-check in the yellow aircraft, because that's the one with the highest priority. So this reduces a lot my action space. Moving forward, the next addition was to change from a backward approach to a forward induction. So in the forward induction, we're going to start in the initial state, and we're going to move forward and map all the contributions of future states by moving forward. So I can go from each state into another state by performing no maintenance check, performing an A check, or performing a C check. In this example, I only have 1 aircraft and I have 1 A check and 1 C check slot per day. And in this forward induction algorithm, we're going to look into the 3 possible outcome states, and we're going to choose one. And I say in a greedy way, well, the best one is not to perform any maintenance. So I'm going to disregard the other outcome states, and I'm going to continue exploring this one. And again, I have 3 possible options, and I see that the best outcome comes from performing a C-check at this stage. So I'm going to continue exploring this state, and then the best option is to not perform any maintenance, then is A, and then I move forward. And by doing this, I'm disregarding a set of possible outcome states, and in this way I'm going to reduce the number of states that I have to check, and I'm going to reduce the memory that I have to use to store all these states. Of course, that this brings some problems, which is I have to guarantee that at the end I'm working with feasible solutions, because by being greedy in the beginning, I may end up being in a state that I cannot have any feasible action possible, and then it is unfeasible, my solution. Or I even may end up being in states in which the outcome is not as good because I've been so greedy in the beginning that I have consequences for the future. And following this forward induction, we have moved into a discretization approach. And to help us with this, we have simplified the way that we represent our states. So what we said a few slides ago was that a standard approach to model these states would be to represent all the attributes associated with each aircraft in our fleet. And those refer to the usage parameters for the A check, C check, and also for the D check. But we can simplify these by looking at how far we are in this interval associated with each one of these checks. So for instance, in this example here, we have the usage parameters at a given state for 1 aircraft of our fleet regarding the calendar days, flight hours, and flight cycles, and we have information of the interval that we have associated with that check, let's say the C check. If we produce a ratio between these usage parameters, each one of them, and the respective interval, we can see how far we are in the interval. Actually, if we compute the maximum, we can see how far we are regarding the interval of each one of these checks. So this one, this 0.55, will go to our usage parameter referring to the C check. And we'll do the same for the A check and eventually also for the D check. So we are simplifying our state space. And this can help us in this discretization. So let's see how we did this discretization in the case that again we do have one aircraft, one A check slot and one C check slot, 10 flight hours and 5 flight cycles if we use the aircraft. And for that aircraft in my fleet, if I am in a particular state, I have 3 possible actions as we have seen: no check, A check and C check. And if I opt not to do any check, I have to update the usage parameters regarding the A check and C check, and I can compute the interval usage. I can do the same thing for the A check, and I can do the same thing for the C check. And I can represent this interval utilization in a 2D representation for both the A check in the Y and the C check in the X. And this will lead to a point regarding the no check, another point in this 2D space regarding the A check, and a third point regarding the C check. And I can discretize my 2D representation into segments, so these squares that I do have here in my 2D representation. And I'm going to compare each one of the actions that fall in each one of these segments. And I'm going to compare the contribution associated with each one of these solutions. So the no check, I'm not performing any maintenance, so I don't have any interval loss, so the contribution is 0. But if I do the A check, the contribution is the loss interval that I do have, in this case, for the A check. So I lose a lot because I only have used 20 flight hours of this A check interval. So 730 flight hours is my interval loss. So when comparing these two solutions, I'll opt to disregard the one from the A check. And in my forward induction, I'm going to continue only exploring the option no check and the option C check because it's in a different segment. And by doing this, I start exploring more and more solutions, but always disregarding the ones that fall in the same segment and have a lower contribution. So in this case, in which I discretize my 2D into 9 segments, so I'm going to work in each stage with a maximum of 9 possible states, and moving always forward, and the maximum I'm going to have per stage is 9 states. This is a smart way to move forward. Has 2 possible implications. One is that although this A check option was not the best at this moment, it may happen that in the future it turns out to be the best option or a better option than a no check. So we may compromise the optimality of our solution, so we have to be aware of that. And the other problem is by choosing this no check, I'm potentially delaying my checks into a moment that I don't have more capacity. So this outcome state that I chose to keep for future stages will perhaps turn into an unfeasible option in future stages. So to address this last problem, Qichen has developed what he calls a workability check algorithm. So an algorithm that checks if a given outcome state will become feasible in the future. By following a greedy approach, that means by allocating an aircraft to a check every time that we do have a slot available in the future, and this is a very fast algorithm to run, we're going to check if there is no aircraft being grounded in future stages following this greedy approach. If this doesn't happen, it means that the state that we are analyzing is workable in the future. It will be feasible without having the problem of grounding an aircraft in the future. If this doesn't work, it means that no other policy will work. So it means that this state that we are considering will become unfeasible in future stages. So we want to disregard this one. So for each segment in our 2D representation, when we have one or multiple outcome states following in that segment, we're going to check if they are feasible. If they are not feasible, we know that we can disregard them and we will not consider them anymore in our forward induction. If they are feasible, if we only have one, we store that one and that's the one that we continue for following stages. If we have multiple feasible ones, then we choose the best as we have seen in the previous slide. So this is a methodology that Qichen has developed in his PhD, adapting the traditional dynamic programming approach to solve this maintenance check scaling problem. And this works. And he has proved that this works in an example that we got from one of our industrial partners, in which we did have 45 aircraft, all from the family of A320, and they do have a daily utilization average of 10 flight hours per day and 5 flight cycles per day. We do have all information about the C-checks intervals and the A-check intervals. We also have information about the lapse types of our checks. So the A-checks will take 1 day. The C-checks will take 7 to 30 days. And this happens because we do have multiple types of C checks and because we consider that our D checks have merged with the C check. So when we do have a D check combined with a C check, it may take more than 1 month to perform this check. It's 5 years prom that we have considered. We have 2 A-check slots on Tuesdays and Wednesdays, and we do have 1 A-check slot in all the other days, except weekends and public holidays. And we have 3 C-check slots in parallel, but only between the non-peak periods, between October and May. So this regarding the Christmas period and the Easter period, and no slots in the summer. If you want to know more about the prom, about the approach, and about the results that I'm going to present here, you can check the paper published by Qichen in 2019. And this is a summary of the results that we have obtained. So we have here an estimation of what the airline will have following their plan from 2018 to 2021. And we have the results from Qichen's dynamic programming-based method here in this column. And what we observe is that we can reduce the average flight hours that we're going to have at the moment that we schedule our C checks and A checks by about 0.2 and 4% respectively. This is a reflect how much we are exploring our interval for both checks. But more important, what we see in these 5 years is that we may end up having 2 less C checks and 33 less A checks. And this represents about $600,000 US in these 5 years that we are going to save only in maintenance costs. And because we have to perform less maintenance checks, we're going to have the aircraft available in the time that we are not doing maintenance. So we may generate more revenue. And this could be about $75,000 per flight hour that we have this aircraft available. In addition to this, we have the benefit of having a consistent scaling approach that takes only 50 minutes to compute the solution for this fleet of aircraft and for 5 years, while the airline follows more or less a manual approach, and this may take several days, up to 1 week, to come up with a full schedule. And every time there is a change in the inputs, they have to recompute the schedule, while using the DP-based method, in 50 minutes we do have a new schedule. So this could be very handy for an airline. And with this, I finished the airline maintenance planning lecture. So I hope it was clear to you why it is a complex problem and why it needs to be part of the airline planning framework. And I'll be happy to address your comments or questions in our Q&A sessions or in the comments below this video. I'll see you in the Q&A sessions. Bye-bye.